Let's start. So we are talking about a convolutional neural network. We learned that in a network that has one layer of convolution is called convolutional neural network. And convolutional layer consists of three parts: convolutional stage, detection stage, and pooling stage. We learned about convolution stage. We learned about detector stage, which is basically like activation function and nonlinearity that is going to be applied to feature maps to the output of convolution. And then pooling stage. So pooling is, as I mentioned in the previous lecture, is sort of summary statistics. You know, you have a feature map and you want to summarize it. To summarize it, you can summarize it in many different ways. You can take average of a region. You can take L2 norm of a region. You can report the max of a region. And so, for example, here, you know, this is if this is the output of detector stage. So in pooling stage, we may want to take the max. For example, the max of 3 here would be 1. And the max of this 3 would be 1, and the max of this 3 would be 1, and the max of these 3 would be 0.2. So the output would be in this stage. So pooling stage, you may have it with the same size of your feature map, or you may downsample. So downsampling will help in many different ways. It helps in terms of computation. Most importantly, and I think that was the main intuition that they wanted to use pooling to reduce the computational power that they needed. But it provides some basically advantages and properties to the model. One of them is that it makes the model invariant with respect to translation. Not invariant, actually, but it makes it less sensitive to the translation. So consider these two cases. In this case, you know, this is the output of detector stage, and this is the output of pooling stage. I'm going to shift all of these bits one to the right, okay? So something here which will appear, which is 0.3, and everything else will be shifted one to the right. So if you compare these two, at detector stage, every single element has been changed. You know, that was 0.1, it's 0.3 now. It was 1, it is 0.1 now. It was 0.2, it is 1 now. So every single element has changed. But look at the pooling stage, and pooling here was max pooling. So we took the basically maximum of 3 elements. So that was 1, it is 0.3, that was 1, it's still 1, that was 1, it's still 1, it was 0.2, it is 1. So everything has changed here, but only 50% of elements after pooling have changed. Why 25%? So among these 4, 2 of them have the same values, and 2 of them have different values. So 50% have the same value. So this basically gives you some sort of intuitive idea that how come pooling can help in terms of translation and make the model less sensitive to translation. And in many cases, actually, it's helpful because you remember, you know, to train a model, one of the things that we did was data augmentation, and we shift, for example, the data to the right, to the left. Or when we talked about the idea of manifold, we were talking about the case that, I mean, imagine that the data that you're working with are samples from a manifold, but the sample is sparse. So there are many other points that could potentially be sampled from the manifold, but you don't have them. And those points are points, for example, that are your point in the original data set and the training set when a translation has been applied to it, okay? So in this case, you somehow take care of these translations, you know. If you have a face, it's a face. It doesn't matter that you shift this face a couple of, pixels to the right or pixels to the left or up or down. Still, your classifier should detect that it's a face of person A, And so being invariant to translation will help. And this is, I don't know if you listened to the talk that I posted on the Piazza. Actually, one of the controversial part is this part. Some people believe that pooling is not a good idea, and they believe that it's not a good property that we get out of it. Okay. Another basically property or another good thing that we can we can gain of pooling is that we can work with input of varying size. If you have any machine learning model, the input to the model is a vector of fixed size. So you have support vector machine, for example. The input is d-dimensional vectors. So it means that your original data or training data should have a fixed size. But in real applications, there are cases that data doesn't have fixed size. So you need some sort of pre-preparation actually to the data to make it the same size. Here, actually, this pre-processing can be shift to the model. You can imagine that images have different sizes, and you do convolution on them, so feature map have different size, right? But at the pooling stage, you can make them all the same size. For example, this is the output of detector stage, and no matter what the size is, I just make it to the 4 part, and I take the max of each part. So the output after pooling would be a vector of length 4, for example. It doesn't matter what the size of the feature map is, right? So it can help in these cases. Okay. So we talked about the relation between feed-forward neural network and convolutional neural network. And we learned that convolutional neural network can be actually seen as feed-forward neural network that are not dense, they're sparse, and some of the parameters are tight. We share parameters. So it can be explained in terms of basically prior. If you think of the word as a Bayesian statistician, for example, then everything is random variable, and you have prior on everything. So think of these variables as some random variable, as weights, as some non-random variables, that you have some priors on them. So prior could be weak prior, could be a strong prior when you have a Gaussian prior, for example, on a parameter with large variance. It's a weak prior. Basically, you let the model, you let the posterior, to choose any value in this range, or even here, with less probability. But your prior is that it's most likely it's here, but could be here, here, here. But I may have this prior. So it forces the posterior to be closer to, what I specified here. You may have infinitely strong. This is a strong prior compared to the previous one, which was a weak prior. You may have infinitely a strong prior. Infinitely a strong prior means that you decide that some sections of this space should be 0 completely, explicitly. I don't allow any probability here. It's not like Gaussian that could take any values with some small probability. I would say no, that it is definitely 0. Okay? Compare L2 norm with L1 norm. When you regularize with L2 norm, like ridge regression, you would say that the vector of my parameters could should shrink, but could have values, close to 0. But L1 norm tell you that no, some of them should be 0. I can't tolerate any values here, even a small. So this is like infinitely a strong prior that some needs to be 0. So you can imagine that a convolutional neural network is a feed-forward neural network when you have infinitely a strong prior which force the model to choose 0 parameters for some of the weights. So it should be a sparse. Some of the weights can't, we don't tolerate for those weights to have any value, even a small. They have to be 0. Yes?
Which stage enforces this?
Sorry?
Which stage of the convolution?
Well, this is interpretation of convolution. In convolution, we enforce this explicitly. In convolutional neural network, we enforce it explicitly. When you have an image, for example, and you choose a kernel, and the size of the kernel is smaller than the size of the image, you're enforcing some weights to be 0, because you're just multiplying this kernel to this portion, If you flatten this image, vectorize this image, and flatten this vector, so this vector will be applied only to this part. This kernel will be applied only to this part, not to the rest. So you decide that the rest are 0, right? And then you start to shift this kernel all over the place. It means that you shift this weights all over the place. So that's another prior that you have. So one prior will make it a sparse. Another prior would say that these weights needs to be shared, I have to just shift these weights over. I can't choose new weights. It's in contrast with dense neural network that weights could be anything, and any weight could be different from the other one. Okay? So in practice, we don't implement convolutional neural network as a dense network with some prior or some regularization or some restriction. We implemented the way that we explained in the previous lecture. But in terms of interpretation, it can be interpreted as a dense network with some prior, a strong prior, or with some regularization. Yes.
So the infinitely strong prior comes from the fact that we only apply the kernel to some parts of the image, and the weight sharing encourages regularity, but it's not really part of this.
Share weighting also comes from the fact that you shift one single kernel all over the place, So these kernels are your weights, right? And so, if you choose the size of the kernel to be the size of the original image, it's dense. And any input can choose any weight, right? But when the size of kernel is smaller, two things will be enforced. One is sparsity. The other one is weight sharing. Okay. Okay. If you have seen in practice, actually, people use tensors to show neural network, convolutional neural network. The reason is that, so far actually we are used to work with vectors as the input of the image. And even sometimes we had input of the model. Sometimes we had an image and we used to vectorize that image as the input to the model. Now imagine that this image is not grayscale, it's color. If it's color, it has 3 channels, green, red, and blue. So basically it is like this, So you have 3 channels. So 3 channels basically means a 3-dimensional tensor, right? It's a 3-dimensional tensor. So imagine this is your input to the model. And then you want to convolve it with a kernel. Then your kernel would be whatever the size of the kernel is. Say it is 3 by 3. 3 by 3, say 5 by 5. It's going to be 5 by 5 by 3, which is going to be convolved with this, right? So in practice, similar to feed-forward neural network, usually we work with a batch of data. So in each iteration, we have a batch. So say, for example, my batch is 10, it's 20. So it's going to be, if I want to show all of these data points now, it's going to be a 4-dimensional tensor now. It's going to be like size of the image, like say it is 64 by 64 by 3 by 10. There's 10 of them. Okay, so that's why people use this tensors when they want to represent a neural network. And it's important to have in mind that when you have these tensors, either at the input or as the output of one convolutional layer or as the output of a pooling layer, when you convolve a kernel with it, the kernel also has a 3rd dimension, which basically will multiply to all of these layers in your data. Yes?
So in your example, with the kernel have 75 unique weights. The weights aren't shared across channels.
Sorry?
The kernel, because you said it was 5 by 5 by 3 channels, so is that 75 unique weights, or are there 25 weights shared across 3 channels?
Unique. Okay. I think I can. Okay. You know, something interesting is that some researchers actually observed that if you assign the weights of kernels by random weights, it's not as good as training the kernels or training the weights, but it's going to work in some extent. It's very surprising. You don't learn the weight of the model. You just draw from a distribution randomly, random weights. But it works to some extent. Why it's supposed to work? Any intuition, any insight to the problem that, you know, I'm not learning kernels. I assign the value of these kernels randomly. I have a network. The weights of the network are drawn from a random, a normal distribution. And the method works to some extent, you know. Yes?
Are you still allowed to learn higher level weights than that example?
Well, you can, yes.
Would it be that even if you randomly sampled your kernels, they still form a sort of orthogonal basis in a lower dimensional space?
Actually, this is a pretty good intuition or insight to the problem. That if in high-dimensional space you randomly select some vectors, what's the chance that they are orthogonal to each other? In high-dimensional space, there's a high chance that they're orthogonal, right? There's a high chance that the features that they extract are independent features or almost independent features, right? So you have a classification problem and you learn weights of the kernel. Means you are learning features that are relevant to this classification problem. But you don't learn them, you just assign some random weights to the problem. The output of kernel after convolving to the image would be some features. Features that you haven't learned, features that are not necessarily relevant to the classification task that you have in hand, but there are some features. But the important thing about these features are that these features are with a high probability, they're orthogonal. Means that they are not redundant. They're not the same they are not expressing the same aspect of the input image. They're expressing different aspects of the input image. And in a classification task, they might help, when you represent, re-express your data in many different ways with many different features. Okay, that's one intuition to the problem. There are actually interesting properties about random projection, and if you have, forget about neural network and forget about convolutional neural network. If you want to reduce the dimensionality of the data from, say, for example, I have d-dimensional data, and I want to reduce the dimensionality of the data to p dimension. So I multiply this vector by a linear transformation, p by d. So the output would be a vector p by 1. So suppose that I have n vectors in d-dimensional space, and I want to, through a linear transformation, I want to map them in p-dimensional space, and my goal is to preserve pairwise distances. So I want the distance between point A and B in high-dimensional space be the same as the distance between point A and B in p-dimensional space. I don't want the distance between points changes. Okay? As much as possible. It's not always possible. When you go from 3-dimension to 2-dimension, sometimes it's not possible to preserve the exact distance between points. But as much as possible, you want to preserve them. What would be the optimal solution to this problem? How do you calculate this transformation?
Set up an optimization problem?
Yeah, you set, of course, an optimization problem, but the solution is something that you know. The solution is PCA. Okay? This transformation is transformation that you can compute from PCA. So it preserves pairwise distances. Now suppose that this is not, it's not PCA, it's random projection. You sample from a random distribution. And this random is Ghodsi, or is Bernoulli. So intuitively, you think that what would happen in p-dimensional space will be a disaster, Points will be in mess, in p-dimensional space. That's what our intuition is, or at least that's what my intuition is, that if this is random. But that's not really the case. By a random projection, you can preserve pairwise distances up to some bound, which is not a bad bound. So somehow, it's not optimal. The optimal is PCA. But somehow, you can preserve the structure of the data through a random projection. This is just a linear projection. What we have in neural network is a random projection, a linear random projection, and then we apply a nonlinearity to this, right? And there is another linear random projection, and there's a nonlinearity applied to this. And there's a paper, relevantly new paper, which proves that, we know that through random projection we can preserve pairwise distances. But they show that through random projection and nonlinearity, you can reduce the distances of one class and increase the distances of different classes. It's not actually based on the class, it's based on the angle of points. Points with small angles will be shrinked, become closer to each other, and with large angle, which most likely are in different classes, will be further apart, which is helpful for classification, right? If you try to collapse point in one class and try to take the points of different classes far apart, it's helpful for classification. And they basically believe that this is what's going to happen if you have some random weights. They prove if for ReLU nonlinear function. Okay, so these are some intuitions or some mathematical reasons that this might work. Yes?
Just for my clarification, why PCA preserves the distance between the data points from the higher dimensional space to the lower one?
Because that's the solution of the optimization problem that we solve for, you know. Basically, you can derive PCA in many different ways. You can derive PCA in terms of maximum variation. You can derive PCA in terms of the best reconstruction. You can derive PCA in terms of preserving distance. You know, if you want to preserve distances, the solution is MDS, maximum is multidimensional scaling. Okay, in multidimensional scaling, if the distance is Euclidean distance, is identical to PCA. So basically, you can see that PCA, as long as your distance is Euclidean distance, PCA and MDS will be identical, so it means PCA preserved distances. PCA has many other properties. PCA has the best reconstruction error. It means if you map on the P dimension, go back, it's optimal. PCA capture the maximum variation of the data. It has many properties. One of them is preserving this. Yes?
I'm just wondering, so what is the effect of choosing different distributions for your, you know, sort of when you randomly choose these weights, right?
Mm-hmm.
There must be some sort of difference between drawing from a normal or drawing from Bernoulli.
Yeah, I mean, the theorem for linear random projection is for normal distribution and for Bernoulli.
So when you randomly initialize weights in some network, do you go for just Gaussian, or are there more
Yeah.
fancy things you can do?
I think you can do Gaussian or you can do Bernoulli. Yes. Projection matrix, yes. It's not a projection matrix, it's a transformation. Yes. Yes. I thought you want to tell me that it doesn't work, you know, because actually Amir spent a fair amount of time working on this randomized network. And it works in some extent, but not as good as we hoped to work. Yes.
So, but intuitively in a high-dimensional space, it also seems that you are more likely to choose a subspace that is along the directions corresponding to lower singular values. That is, you're choosing the subspace that does not capture a lot of variability of the data.
In which scenario? Sorry, I didn't get that.
So if you're choosing vectors from a high-dimensional, if you're working in high-dimensional space,
Mm-hmm.
if you're randomly choosing, then intuitively it also seems more likely that you'll be picking some subspace that does not capture the maximum variability or high variability of the data.
Why?
Because basically let's say you're working in a 100-dimensional space, and then you might just have three or five principal directions that capture the maximum variability. But if you randomly sample, then what if you end up with a subspace that does not capture, that is not along those directions? So you would end up projecting in a way such that you don't capture the variability of your points, right?
So I told you that at least for me, it's sort of counterintuitive. You know, intuitively, I would say that it's gonna, you know, make a mess after transformation. But that's not the case. At least it doesn't align with my intuition. And I think your question is about the intuition, that intuitively it doesn't seem to work. So I'm with you. I mean, my intuition doesn't tell me that it should work. But it works in practice, and you can mathematically show that why it works. This is based on, this is the base of compressed sensing as well. And compressed sensing was a very hot topic for a while. One of the very basically, popular and pretty, well-received paper in that area was, what was the name? Single sensor camera. The idea is that given this P measurements, you can recover these D measurements if you add some sparsity structure to this, okay, in compressed sensing. And now imagine that you have an image and you want to take a picture of this image and with high resolution, but you only have one single sensor. You don't have 6 million sensors. You only have one sensor. Okay, so what if this is Bernoulli? Means some of them are 1, some of them are 0, right? And matrix multiplication here means that when you have 1, you keep this element. And when it is 0, you knock down this element. And then you add them up, right? So make physical realization of this matrix multiplication when this is Bernoulli. So make a filter here that this filter randomly has some black parts and some transparent parts. Okay, so this is black, and the rest are transparent. And randomly change those. And put it in front of your image. And the output of the image, whatever it is, comes to a physical lens. And so it's like adding all of these elements, So physically they will be added, and there's a sensor here which will sense this. And that's going to be one element here. And then you repeat this process P times. So you have P measurements. And based on the theory of random projection and theory of compressed sensing, you can recover this D, which is your original image. So you can have an image with high resolution with only one sensor. So anyway, that's not the topic of our discussion now, but I just wanted to tell you that it works. And there are two versions of that. Actually, one is to assign weights randomly. The other one is to learn weights, but in a sort of unsupervised manner, not through backpropagation. So use some pre-calculated weights or pre-calculated kernels. And the way that, there are many different variations of that, but one variation is to use PCA actually to do this. And the idea is that, say this is my image, original image, then I'm going to split this image, or take the patches of this image, like say patches of 3 by 3, when they have overlap. It's like a kernel sliding all over the place, right? So I take these patches and I make a data set, a large data set. And then I do PCA on that. And I choose eigenfaces as my kernels. So each eigenface basically is supposed to give me one direction of variation, That eigenface, which is 3 by 3, would be one kernel. So the second eigenbase would be my second kernel. That's another way of computing kernels in sort of unsupervised manner. Okay. This one is not that popular in practice. Using random weights is popular, but not for training the whole network. There are models that assign the first couple of layers randomly and learn the last layer, for example. So basically, they assume that some features have been learned randomly, and now the last layer, which is a dense layer, or the last couple of layers, will learn a classifier using these random features. Okay, but it is useful sometimes when you are designing and a network, the configuration of your network. You don't know really, you don't know that, do I need 2 layers of convolutions? I need 5 layers of convolution. What would be the optimum size of the kernel? So there are many parameters that I have to play with. And training a network is time consuming, right? And it's pretty time consuming to come up with a structure, like say 3 layers of convolution, 2 layers of dense, and train it. It takes, a while. And then I decided, no, it's not a good one. Let's go for 4 layers of convolution and 3 layers of, or change the size of the kernel. So it's very time consuming. So in this stage, set the weights randomly. Don't learn them. Compare different structure with each other. Come up with the structure which has better performance when you compare them. When you then fix this structure and try to learn it now. With random weights and random kernels, try different structures, then fix the structure, learn the weight. Okay, any question? Yes.
Of these structures that you select, how do you know which kernel is performing well for you? Like, could you give an example
Of?
Let's say, face detection?
Mm-hmm.
Yes, so you have 3-4 kernels with you and many kernels with you. And how would you say like the outlines, whichever kernel has a much more well-defined outline?
No, you are talking about random kernels?
You said we have to select a good kernel which is...
No, select a good structure.
Structure, as in the weights for the pre-calculated weights.
I'm debating between 2 structures, for example. I'm debating between 2 structures. This structure has 3 layers of convolution. And this structure has only 2 layers of convolution. I don't know what to do, right? So instead of learning these 2, I will set the weights randomly here and compare these 2. And it seems that this one works better. Then I go and learn the weights for this.
One thing, what is the meaning of that last line? Use features that are not trained. What does it exactly imply?
The explanation that I had for PCA, taking patch of the images and then apply PCA. So these kernels are basically are learned based on they are learned, but they are not random, but on some sort of unsupervised manner. Yeah, so one of them is just initialize them randomly, and the other one is unsupervised learning. Okay. So let me show you an example now. So similar to, I showed you an example in Keras for feed-forward neural network. This is an example for convolutional neural network. A part of that would be pretty similar to what we have done for feed-forward neural network. So at the beginning, you have to import some libraries and set some parameters and so on. So this part would be similar. So you import the libraries that you need. Set parameters, for example, here I would say the batch size would be 256. It's a parameter, right? Number of clusters here is 10 because the data set that I'm going to use here is CFAR10. CFAR10 is a data set which has 10 different objects in it, like cars, airplane, and so on. So the number of classes is 10, and well, the number of epochs I have to set, I would like to repeat this for 100 times. Then I have to load data similar to the previous example that I told you. If you don't have MNIST, Keras has MNIST itself. It has many data points. It has CFAR. So CFAR has been loaded at the top. Here you see I import CFAR10. And here the same as we did for feed-forward neural network, I can make a test set and training set out of this. So if I make a training set and test set out of this, and then print the shape, you see that the trained shape would be 50,032, 32, 3. So it means that, you know, it's a tensor, four-dimensional tensor, right? I have 50,000 images. Each image is 32 by 32 by 3 because it's not grayscale, it's colored image. So it has 3 channels, green, blue, and red. And it's 32 by 32. So each image is 32 by 32 by 3, and I have 50,000 of them. And I have 50,000 training sample, and I have 10,000 test sample. So we did a little bit of pre-processing for feed-forward. We do the same thing here. Change everything to float 32, which helps in terms of computation. And then we normalize it, divide everything by 255. So that's exactly what we did for MNIST data. Here, actually, I just want to show you some examples of this data set. These are examples of data set, you know, that's how this data set looks like. So colored images in different classes. So car and, you know, animal and so on. It's not a trivial data set like MNIST. Okay. So if you remember in feed-forward neural network, we converted our labels to one-hot vectors. We do the same thing. We have a function here to do this. We can convert each of these labels because labels are between 0 and 9. So we can turn them to one-hot vector. So my label would be from now on, after running this, would be a vector of length 10 for each class. This is new, actually, data augmentation. In regularization, we talked about data augmentation, which helps in terms of training. And in data augmentation, the main idea is to transform data slightly, shift them, translate them, rotate them, and so on. So, in fact, you don't need to do it explicitly. It doesn't mean that if you have 1,000 point data augmentation doesn't work this way, that you have to generate some new points and explicitly add those points to your training set. You can do it at the time of training. The way that it works is that we have this function image data generator, which has many parameters, and you set some of these parameters. These parameters will tell you basically that do you need to rotate, do you need to translate. If you want to translate how many pixels, rotate how many degrees, add noise. You have many different options, which you set those options that you want to true or set some of them to false, and set how much shift you would like to apply to data. But you never generate them. At the time of training, basically the network, you are going to fit the network by the output of this image data generator. Okay, so like in one iteration or in one epoch, the original data are going to be used. In next iteration, this function will be applied to the data, and it's going to rotate the data slightly, and then the network will be fit with that one. Okay. So you don't need to explicitly generate some data, but it's going to work basically at the time of training by implicitly generating some data and fit the network with transformation of the data. Okay, so it's very useful.
I'm sorry, does image generate a custom function or?
No, it's built in. It's built-in function in Keras. That's going to be the structure of the network that we are going to use. So the input is 32 by 32 by 3. So each image is basically a three-dimensional tensor. Then I'm going to have 2 layers of convolution. So 2 layers of convolution will be applied. Based on the number of kernels that I'm going to apply, the third dimension of this feature map will be different, right? Say, for example, I choose a 3 by 3 dimensional kernel. How many kernels I'm going to choose, if I convolve this is 32 by 32. If I convolve this by 3 by 3 kernels, the size of output is going to be 32 by 32 if I have padding. You can have padding when you do convolve, or you may not have padding. Padding means that you have this 32 by 32 image, and if you just start to convolve this with 3 by 3, the size would be less than 32 by 32. But I can do padding in the sense that I can add some pixels here. And when I convolve this way. Okay? Padding could be 0 padding. I may add zeros, or could be same padding, means I just duplicate this part. So if I do it with padding, the output image would be 32 by 32. So I have 32 by 32. I convolve it with 3 by 3, so the output will be 32 by 32. But how many kernels do I apply here? If I apply 10 kernels, what would be the output? With one kernel, I have 32 by 32 feature map. If I apply 10 kernels, then it's 32 by 32 by 10. I have 10 feature maps. One feature map for each kernel. Okay? So that's actually what happened here. The first convolutional layer, the size of the kernel was 3 by 3, and I applied 32 of those to the model. So this is 32 by 32 by 32. So then I have another layer. This is also 3 by 3, and I have 32 of them. So again, when this is 3 by 3, it's actually 3 by 3 by 32, which will be applied to all of these 32 feature maps, and will generate one element of the new feature map here. But I have 32 of them. So it will generate another 32 by 32 by 32. Okay? So that's my next layer. And so for the first one, I have padding, same. For the second one, I don't have padding. For the first one that I have I have padding, the output, the feature output would be the same size of the input. So it would be 32 by 32. For this one that I don't have padding, it's going to be smaller than 32. It's going to be 30 by 30, right? You don't have padding. And you define the size, the type of activation function. In the literature of convolutional neural network, this is basically your detector, this activation function. Now I do pooling. In Keras, everything is a layer. So pooling is a layer. So you just add a pooling layer. In this pooling layer, the pooling size is 2 by 2, and the type of pooling is max pooling. So it is 32 by 32. So I take 2 by 2 region, and I take the max of that. So if it's 32 by 32, after pooling, what would be the size? If this is 2 by 2. Yes, it's going to be 16 by 16, right? Yes.
So there's no overlap between these,
Between what?
the 2x2 pooling window? Like
It
the
depends
kernels
on your. It depends on your struct. You know, depends how you define your struct. Then here actually we had a dropout, and dropout is just a layer. You know, Keras. So this is a convolutional layer, another convolutional layer, pooling, and we don't show the dropout here. Then there is two other convolutional layer that has been added after. These two convolutional. There is these two convolutional layers that have been added. The number of kernels that we are using here is 64. The size of the kernel is 3 by 3 again, but the number is 64. One of them has padding, the other one doesn't have. So if it is 16 by 16, after I apply this convolutional layer, you know, this is 16 by 16 by 32. So I apply 64 kernel with size of 3 by 3 with padding. What would be the size of this? So 16 by 16, kernel 3 by 3, I have padding. The output feature map, what's the size of the feature map? 16 by 16. I have 64 kernels. So I have 64 kernels, so I generate 64 feature maps. So this is going to be 16 by 16 by 64, right? Okay. Another layer of 3 by 3 kernels, but 64 of them. So it generates another 16 by 16 by 64. If I have padding, if I don't have padding, it's going to be smaller than 16 by 16. But it's going to be 64. So again, I have a layer of max pooling, 2 by 2. So it's 16 by 16 becomes 8 by 8. Okay, so that's the pooling. And I have a dropout layer here after this pooling. Okay, now it's pretty common to have a couple of dense layer at the end, you know. Use convolutional layer for feature extraction, and then use some dense layers to do classification, for example, or do regression. Actually, recently, there are models that are called full convolutional models. There's no dense model in them. Everything is convolution. You know, convolution actually is gradually takes the territory of everyone, you know. It was actually a restricted Boltzmann machine first. Then people learned to train a model, a deep model, without assumption of restricted Boltzmann machine. So they don't use restricted Boltzmann machine anymore. Convolutional neural network, they learned that, you know, it works way better than feed-forward neural network in terms of feature extraction. So it's pretty common, but you want to do classification, you need some layers of dense. Then there are papers recently which shows that, okay, even for classification, you don't need dense layers. You can do classification with, you know, some convolutional layer. And for temporal data that we are going to learn later on in this course, next lecture is RNN. Again, I mean, RNN was, you know, the main model that we use for temporal data, like for text. But there are many models now that they use convolutional network for modeling temporal data like text. And they claim in some cases it's better than others. So, yes?
How do you specify the convolution layer with fixed weights?
With fixed weights?
Yeah, not to be done.
I mean in Keras?
Yeah. Yeah.
Without, yeah, I'm not sure actually in Keras how you do that. I'm not sure in Keras how to do that. Do you know?
I didn't answer the question.
You don't want to learn weights. You want to weights to be fixed or be randomly select them in Keras.
That you can choose that these parameters are not there anymore for training.
There's a list generally and it's a variable, and in that list you can pass it in the train function.
Mm-hmm.
So as a parameter, so it doesn't train it.
Okay.
It trains on it.
So if you want to do it, either you have to Google or you have to ask one of these three people. Okay. So we want to have a couple of layers of dense, right, as a classifier. We are going to flatten whatever we have here. You know, this is like 16 by 16 by 64. I'm going to vectorize it. So treat it as a vector. So if there's a function in Keras which flatten this, you know, make a vector out of the 16 by 16 by 64. So this is a vector now. And okay, so I have a vector. I can add some layers of dense after that. And this is one layer of dense, for example, here, which has been added. A dense with number of classes and activation function is softmax because I want to treat the output as probability. Okay. Okay, yes.
So the flattened version, is that the feature vector?
Sorry?
The flattened layer, that's the feature vector?
So you flatten the feature vector.
Okay.
You know, these are all basically all feature maps that you had along the way. At the end, you have another feature map, and you do pooling out of that feature map, and you reduce the size of that feature map. Now, this is my final feature that I want to do classification on it. I vectorize it. I feed it to a classifier, which is my dense model.
Which is essentially an MLP.
Sorry?
Which is essentially an MLP in this case, right?
Yes.
It normally goes on.
Yeah, it's a feed-forward neural network, or MLP. Yes, these last layers. Yes.
Now, when you want to start backpropagating to complete the training cycle,
Sorry?
for the backpropagation part of this entire cycle of structures,
Mm-hmm.
will you be backpropagating completely after you flatten the entire thing and finally learn your
Yes, yeah. Yeah, from end to the
Okay,
begin.
if that is the case, then now the data set you had 10 pictures of aeroplanes, 10 pictures of cars and everything. Now when you feed 10 images of aeroplanes, you obtain your 10 images and then you flatten your final feature learning of these 10 aeroplane images, right? Wouldn't you have done that already? By flattening, wouldn't your data be garbled by combining the feature learning that you've done previously? You're not treating each aeroplane image discretely, right? By flattening, you're
I'm not
combining-
sure actually if I follow your question. You know, you're treating the model as like batch learning. You give a batch of data, and this batch of data is not all airplanes. So the different things, you know, randomly selected, different objects. And you feed it to the model, and you go forward, compute the output value, and then backpropagate. Update all of these weights, and next batch goes in.
I got that. And the intuition behind flattening, and let me get the intuition behind flattening.
Intuition actually is that you have, you know, you want to do classification. You need a classifier, and you decided that your classifier is going to be a feed-forward neural network. What is the input of the feed-forward neural network? It's a vector. So this 16 by 16 by 64 is your features now.
Only if you want to feed forward neural network,
Yeah, you flatten. If you want to add more convolutional layer, you don't need to do it. Yes?
So are you learning the kernels?
Yes.
Or the kernels fixed?
Yeah, no, kernels are not, I mean, kernels are the parameters of your model.
Okay, so you're learning the 3 by 3
Yes,
into.
yes, you learn all of these. Yes.
Just earlier in the lecture, you said that all convolutional layers have a pooling stage.
Not necessarily.
So do these sort of the pooling stage, and Conv 2D doesn't have.
You know, these are 3 elements of a convolutional layer, but not necessarily you're going to use
Yeah, it's more of an implementation.
all of them.
function.
Even you may decide not to use activation function, you know. You may decide to apply just a linear, to do convolution and then do pooling, just convolution. You know, if you don't do convolution, then it's not a convolutional layer. But between pooling and activation, basically, it's your choice. Usually, activation is there every time, but pooling is your choice. You may choose not to do pooling. Yes?
Just a quick question. Is it fair to say that max pooling is similar, is sort of dimensionality reduction?
What? I'm not sure actually if it's dimensionality reduction.
The way I'm thinking is that
Um,
the convolution.
Well, actually, it definitely reduced the dimensionality, if that's what we mean by dimensionality reduction. So it reduced the dimensionality. So whatever the dimensionality was, it was 32 by 30. No, it's 16 by 16. So I reduced the number of variables that I have definitely.
Because I'm thinking in respect to convolution autoencoders,
Mm-hmm.
and that's strictly for dimensionality reduction.
Yes.
And the way they do that is by max pooling to reduce dimension. So
Mhm.
is it the same ideology?
Well, it doesn't need to be by pooling, you know. You can have autoencoder with feed-forward neural network, for example. You can reduce the number of weights. You can have just convolutional layer with the less number of kernels, for example. It doesn't need to be pooling, definitely. But if by dimensionality reduction, you mean that we reduce the dimensionality? Yes, we do reduce the dimensionality after pooling. But if you want to compare it with dimensionality reduction techniques like PCA and LLE and isomap and this type of thing, it's not dimensionality reduction in any systematic manner, you know. Just summarize the data. I think the best way to put it is that we summarize the data by reporting some statistics of the data instead of the original data. Okay, so now we have to compile the model, and at the time of compile, you define what the objective function is. For example, in the previous case, our objective function was just L2 norm. Now it is cross entropy. If in the previous example, I think the accuracy was about 93%. Just change the objective function in the previous example to cross entropy, and the accuracy would be about 97%. You know, so objective function is important. So it's cross entropy, and then this is the summary of the model. That you can see that, for example, we had 32 by 32 by 32 as the output of the first layer, and the second layer didn't have pooling, it didn't have padding, so it becomes 30 by 30 by 32, and then we had a pooling, so reduce the size to 15 by 15 by 32, another layer 15, 15, 32, and so on, you know. Then we had another layer which didn't have padding, so it reduced the size from 15 to 13, and max pooling became 6, and then we flatten everything. So it basically gives you what the structure is. It's a good practice to make sure that the model that you have is basically what you wanted to have. So, and then you have to feed the model, means training. So training in this case is going to be time consuming. It's going to take a while. You can see the accuracy is 0.1. And if you go with 100 epoch, then it's going to be about 80-something%. So gradually model learns, but it's a time-consuming process. It's in fact, actually, it's not running on this laptop. It's running on a machine with 2 GPUs. Still, it is slow. Yes. I thought you have a question. Okay. So the rest of the class would be just watching this, make sure that it trains, right? So I would like just to let it go for just one. Okay, see that the accuracy becomes 0.4. Sorry, 0.2. Then the accuracy becomes 0.3. So it improves. Yes.
What's the question? Oh, what's the difference between the accuracy and the bar accuracy on the first one? Because before it's like 0.23, but now
that's accuracy. One of them is accuracy on the training set. The other one is accuracy on the validation set.
Oh, okay.
Okay, so try this later. I'm just gonna interrupt this. So I interrupt the process because it's sort of time consuming. But after training, I just saved the model in this file. So I just load it, as if we waited and everything has been trained. Now we can apply our model that has been trained now on test data. So by this function predict, you can apply it to X test. And if I apply it to X test, and then the output would be one hot vector of length 10. So I need to look at the argmax of this and find corresponding class. And then basically, we had the labels, we turn it to one hot vectors. Now we have one hot vectors, turn it to, or we have probability, not one hot vector. We have a probability vector of length 10, turn it to class label. And this is what we have predicted. This is true Y test. Compare them. In this actually example, this 10 examples, it seems to be perfect. Everything have been predicted perfectly. But if you look at the test accuracy in general, it is 0.82% is the accuracy. This is pretty hard problem, Try this CFAR10 with models that you learned before. One good thing about neural network is that it's back-to-back model, means that you feed the data, the raw data, and you get the output. If you want to apply any other techniques, you need lots of pre-processing. You need a way to extract features from the data and feed it to a model, a classification model. But here, actually, the model will take care of feature extraction and choose those features that are relevant to class labels that you have, or to the regression problem that you have, to the problem that you have in hand. It will choose the features relevant to that. So that's one good thing about it. Even try feed-forward neural network that you learned before on this data set. Change MNIST with CFAR10, and you're going to see that it doesn't do well, really, because it's a complicated data set. So it's pretty powerful model, yes?
What's the usual size of kernels? Since the 10 by 10 kernel would be too much.
There is no usual in neural network, Everything is allowed. You can do whatever. There are common practices here, like this 32, 64, 128. People usually choose, 2 to the power of something as the size of the layer. Kernels are, kernels supposed to capture local structure. So if you choose a large kernel, it defeats the point, It's as if you have a dense network. So when you choose the kernel to be large, you are approaching to feed-forward network. So there's no point, actually. So it basically, intuitively, shouldn't choose very large kernels. It should be a small. But anything is up to you. It's more art than science, You have to. Okay, any other question? Okay, everyone have a group now? You formed your group? You have selected your final project? Who has SharkNet account now? Who doesn't have SharkNet account yet? Okay, go and get one. Download the data, really, Start early. It has a very awkward interface. SharkNet, it's not user-friendly.
I've met a lot of people who have accounts, and I haven't met a single person who's used it, actually.
Yeah. At least 2 out of those 3 people that I mentioned at the middle of the class have used that. You can refer to them as well. But yeah, it's not user-friendly, but that's basically what we have here. You can start with Jupyter Hub, but definitely it's not going to be sufficient for your final project. If you have a large data set and if all of you wants to run something last night, it's going to break, So start early and get familiar with Compute Canada. I don't want to scare you, just I want to warn you to be ready. It's not anything complicated. I mean, neural network. Okay, you can stop actually.